Everyone. So today I'm going to present the second class of reagents in organic synthesis. So welcome all of you to the second class of reagents in organic synthesis. So in this session we also discuss about some oxidation reaction which you have learned in the course. So we'll briefly discuss about that oxidation reaction and then we'll solve some questions. So first we'll discuss about oxidation by CAN. So CAN is nothing but sodium ammonium nitrate, where sodium present in plus 4 oxidation state. So it oxidized and goes to plus 3 oxidation state. So it's oxidizing again. That's why it's self-reduced to plus 3 oxidation state and oxidized any alcohol to aldehyde or any other reaction. So in these cases, we also use some another oxidizing agent such as sodium bromate NaBrO3 or TEMPO, which maintain the catalytic cycle. So we here what TEMPO and sodium bromate was will done. So TEMPO and sodium bromate further oxidize cerium 3 plus to cerium plus 4 oxidation state and maintain the catalytic cycle. So as we are using catalytic amount of CAN. So what is TEMPO? TEMPO is 2266 tetramethyl pyridine N oxide. The structure is so this is a radical initiator. So in this case of CAN, it oxidizes through radical mechanism. Radical mechanism. So where it's donate one of its single electron and oxidize any alcohol to aldehyde or ketone. So it has some basic mechanism. The mechanism goes through radical pathway. So the uses of scan is it first oxidize secondary alcohol. So in this structure, there are two type of alcohol. This is secondary alcohol and this is primary alcohol. So in case of CAN, it selectively oxidize secondary alcohol to ketone. So it is very important. So it's selectively oxidize secondary alcohol to ketone, not the primary alcohol remain as such. Some other application is oxidation of allylic and benzylic alcohol. So this is the benzylic position where the alcohol is connected to the benzyl ring, and this is the allyl position. So this group is allyl, and this alcohol is connected to the allylic position. So can selectively oxidize benzylic and allylic alcohol to ketone or aldehyde. So these are the second use. So in these cases, the oxidizing agent is used as TEMPO, which oxidize cerium plus 3 to cerium plus 4 to maintain the catalytic cycle. And in these cases, sodium bromate is used. So what is sodium bromate? O minus Na plus. So this is used to oxidize to maintain the catalytic cycle and further oxidize uh, cerium 3 plus to cerium 4 plus. So these are some other application of CAN. So here what is happening? The benzylic with this position is benzylic, the benzylic hydrogen or the active methylene hydrogen. So this is the active methylene group where the carbon is connected to activated carbonyl, this one and this one. That's why it's called, we call this is active methylene. So this is a methylene. So what is methyl group? Methyl group is CH3 and methylene group is CH2. So this is the active methylene group. So in these cases, both oxidize to ketone. And here, in these cases, the active methylene group is converted to ketone, but in the tertiary carbon, where the benzylic methyl is present, the can oxidize this carbon to alcohol. So this is forming 3-degree alcohol. It can't form ketone because the valency of the carbon is satisfied here. So this is the valency of carbon is 4. So it can't further oxidize to ketone or any other of the state. So next we will discuss about DDQ. So DDQ is 2,3 dichloro 5,6 dicyano 1,4 benzoquinone. This is the structure of DDQ. So at this two chlorine are attached to 3 position and this cyano is attached by 5,6 position. So the application of DDQ is first is greatly applicable in aromatization reaction. So the compound which are non-aromatic in nature in presence of DDQ under reflux conditions such as benzene or toluene aromatized. The mechanism could be so the, in both the cases the hydride is transferred to the benzoquinone and it form quinone to quinol conversion happen here. So it converted to O minus cyano cyano. So it fully aromatized. So quinone to quinol conversion is happened here. After that, so after getting this will form carbocation here at transfer hydride. This carbocation will form. So now there is a hydrogen. So now this O minus of the benzoquinone form abstract this proton and form a double bond here. So it will goes to this. Further one equivalent of quinone or further oxidize this position and form the saturated carbon. So this is tetrahydrocarbonyl convert to carbonyl. So another application of DDQ is the oxidation of benzylic position. So this is the benzylic position. So it oxidized to ketone through the DDQ. So it is happened in these cases we are seeing that this the above one hydride is transferred, but in these cases it happened through radical mechanism. So first one radical is formed and that react with DDQ and form this radical. So then it further the oxidize to alcohol and then ketone. So it happened through radical pathway. So in these cases, the very important reaction, the deprotection reaction. So any benzene group is this one CH2PH. So the CH2PH called benzene group. So this is reprotected by DDQ. So this also happens through radical mechanism. So the first this benzene CH2PH oxonium ion will form, and first it will through the DDQ single electron transfer, it will form this oxonium ion is formed first, and this will quenched by water. So after reaction of water with this oxonium ion, it will form this and OH. So now this alcohol is pushing the electron and deprotect this benzene group. So after benzene goes to benzaldehyde, and it will form the protection happen, and it will form alcohol. So now next we will discuss about the selenium oxide mediated oxidation reaction. So selenium, I will discuss about the selenium oxide mediated reaction. So in these cases also benzenic or allylic position is oxidized by selenium dioxide. So it happened through 2,3 in reaction followed by 2,3 sigma tropic reaction. So the mechanism is, so the benzenic position is this one. So in presence of selenium, there will happen a in reaction. So this is the in reaction. So it's nothing but a 4+2 type of cyclization reaction. So now the selenium goes to OH, and the double bond will form there. Now 2,3 sigma tropic reaction happen here. Sorry, a little. Is now 2,3 sigma tropic reaction happen. So this is one, one, two, three, two. So this coming from 1 to called this 2, and this 1 to 3 called this 3. So that's why it is called 2,3 sigma tropic reaction. So after 2,3 sigma tropic reaction, this will form, and in presence of water or hydrolysis condition, this will goes to the alcohol flow. So this is the mechanism of the selenium dioxide. So it will proceed through in reaction followed by 2,3 sigma tropic reaction. So in one more application of selenium dioxide is it the alpha oxidation of carbonyl compound. So this is the alpha position of carbonyl. So it oxidized to aldehyde. So in presence of this selenium dioxide, same reaction mechanism proceed here. In reaction followed by 2,3 sigma topic reaction. Next we will discuss about manganese dioxide mediated oxidation. So manganese dioxide, the structure is this one. So in these cases, radical mechanism happen for oxidation of any allylic or benzylic alcohol. So this is the benzylic alcohol, benzylic vinyl alcohol. So in presence of MnA2 in dry ether, it oxidized to ketone. So here what happened? This alcohol has homo, homologated cliff and form this O radical. This also cliff. So now this radical form. After further radical mediated quenched, give this ketone here. So it also so radical mechanism proceed for the oxidation of any allylic or benzylic alcohol to ketone for MnO2 cases. So it also oxidation of saturated alcohol. This is the saturated alcohol, so no double bond is here. So it further oxidized to ketone in presence of MnO2. Oxidative cleavage of cis trial. So this is cis trial. Both the alcohol in the same plane or same direction, wedge bond and dotted bond. So it also cleaved in ketone in presence of MnO2. So one more oxidizing agent is the silver carbonate. Silver carbonate on silite. So it's called Petillon's reagent. So oxidation of in allylic or benzylic alcohol. Uh, in these cases, sorry, this is written wrong. So secondary alcohol oxidized to ketone in case of silver carbonate or silite condition. So here this is the allylic alcohol. This is secondary alcohol. This is primary alcohol. So first reactivity order is the allylic or benzylic, then secondary, then primary. So here first presence of one equivalent of silver carbonate in allylic alcohol oxidized to ketone. Then if we add more one equivalent of uh, silver carbonate condition, the secondary alcohol oxidized to ketone, then primary alcohol. Next is the TPAP condition. So TPAP is tetrapropyl ammonium perglutinate. This is a Gillian-Griffith reagent. So this is the butyl propyl group, and this is the structure of TPAP. So it oxidizes the primary alcohol. So in this structure, this is the primary alcohol. So it oxidizes to ketone. Next reagent is the DMP oxidation. So this is Dess-Martin iodine. So this is the structure of Dess-Martin iodine. So it prepared through 2-iodobenzoic acid. So in presence of oxone in heating condition, it first form 2-iodobenzoic acid to IPX to iodoxybenzoic acid. So this is 2-hydroxybenzoic acid, IBX. Now in presence of acetic acid or acetic anhydride, it forms the desmethyl thiodiene. So this is also oxidized primary alcohol to aldehyde. So now if we solve some problem. So first question is the DD2 oxidation of these two cyclohexane. So what will happen here? So if we write the chair form of these two structure, first I will discuss about the trans one. So this is the trans form and methyl and hydrogen is in the trans form. This is the ketone. So there are hydrogen are there. So what happened in presence of DDQ? Sorry, plus 2. This is the trans form and the cis form is what happened here. So in these cases, there is hydrogen and this is the methyl CH2 or the cyclohexane methylene and this is the, so this is the ketone. So in this, so in this form, so this is the one, this is two and three. This one, three methyl and hydrogen steric elements happen there. So that's why the oxidation happen through this position. But in these cases, there is no such steric igneous 1,3 steric interaction there. So that's why this in these cases oxidation happen through this position. So if we write the mechanism, so what happens? So these two hydrogenate are giving their hydride to DDQ. So what is happening in this? In the cis form, we are seeing due to the 1,3 interaction, this this one hydrogen and three CH2 interaction, steric hindrance happen. That's why first hydrogen hydride donation happen of cis form with hydrogen one, this hydrogen. But in these cases, the trans one, there is no such steric hindrance. So that's why the hydride donation happens through this. Sorry. So due to the steric hindrance, in the cis form, the hydride donation happen through this hydrogen one. But in the cis form, there is no such steric trans form, there is no such steric hindrance. So the hydride donation happen through this form, this hydride. So that's why we are getting double bond here in trans form and here in cis form. So this is due to the 1,3 1,3 steric hindrance giving these two different products in presence of DDQ, oxidation condition. The second question is, I think this is clear. So first we'll write the structure of the cyclohexane in the chair form and then the steric hindrance that will affect the DDQ oxidation. So this under DDQ oxidation, the ketone is formed alpha beta unsaturated ketone. We all know. So there is two possibilities: this side or this side. So in case of cis form, due to the steric hindrance or spherical interaction of this hydride or this in the CH2 form of this cis group, uh, persists the DDQ mediated oxidation or this hydride donation by this hydrogen, or in the trans form due to no such steric hindrance, this hydride is free, so it can easily donate to the DDQ. So that's why we are getting the B is the right answer. The second question is, can is now can is how many electron oxidant and which type of catalyst. So we all know cerium plus 4 goes to cerium plus 3 oxidation state. So it is a one electron oxidizing agent and has it has a nitrate group, so it can act as a Lewis acid also. So it also coordinate with any carbonyl compound, so cerium 4 plus by Lewis acidic source, which shows Lewis acidic behavior. So this is the right answer, Lewis acid and one electron. Next question is cerium, selenium dioxide and manganese dioxide oxidation proceed via which mechanism? So we previously discussed selenium oxide goes through in followed by sigma 2,3 sigmatropic rearrangement, whereas manganese dioxide proceed through free radical pathway. So if we see the mechanism of any allylic alcohol, allyl glycation is oxidized to alcohol in presence of selenium dioxide or any primary alcohol oxidized to aldehyde in presence of manganese dioxide. This is brought to single electron transfer reaction. So that is the radical pathway. So the mechanism, if we discuss previously also discussed, so now we can also discuss this mechanism. First, the in reaction. So this selenium is will react through in pathway. This will form this. and now followed by 2,3 sigma topic rearrangement within this product. Now under water treatment will form this alcohol. The next question is, and we all know the free radical pathway for the MnO2 oxidation. So the mechanism, if we discuss, this will go under manganese dioxide. So this hydride is abstract and manganese is this will come. Now further breaking of this an abstract proton from the manganese will give you the aldehyde. This is the mechanism of manganese dioxide. Next question is, there are two types of alcohol, secondary alcohol. This one is the primary alcohol. So there secondary alcohol is oxidizing, secondary alcohol oxidized to ketone, right? So in presence of Ag2CO3 and secondary alcohol is oxidized to ketone, but not in case of DDQ. DDQ silver carbonate can also do secondary alcohol oxidized to primary alcohol. But DMP will oxidize primary alcohol fast than secondary alcohol. MnO2 same primary alcohol first and secondary alcohol. So the right answer is the second one, silver carbonate and sodium ammonium nitrate. Both oxidize secondary alcohol to ketone first than primary alcohol. So the next question is Ag2CO3 on sea life. So there are three type of alcohol is there. This is allylic, this is secondary, this is primary. So silver carbonate, the reactivity order is for silver carbonate, allylic or benzylic. Much greater than secondary, much greater than primary. So first allylic and benzylic alcohol oxidize, then secondary alcohol, then primary alcohol. So the right answer is this one here. First allylic alcohol oxidized to allylic ketone. Then in this cases, secondary alcohol is oxidized. This will not happen. Here both allylic and secondary alcohol oxidized. This is also not happen. So if we use excess amount of silver carbonate, then both primary, secondary and allylic alcohol oxidized. In this cases, primary alcohol oxidized. This is also not happened in case of silver carbonate. But if we use manganese oxide or IBA or DMP, the primary alcohol gets oxidized to aldehyde. So in these cases, selenium dioxide and ethanol condition. So what happens is that in presence of selenium dioxide, we all know allylic or benzylic position oxidized to alcohol. So here three type of allylic position is there. This one, this is two, and this is three. So in the three cases, there are two possibilities: 3A, 3B. 3A is the cis form, 3B is the trans form. So in all the cases for that where multiple option is there for allylic oxidation, so we have to see the steric matters. So which one is the sterically accessible will first oxidize, then the sterically hindered one. So in all these cases, this is there are two proton is there and one methyl group, CH2 group. In these cases also two proton, one CH2, one CH. So in these cases, methyl group has three proton. So this 2-methyl is free compared to other two position. So this methyl 1 and methyl 2 is more free sterically accessible than these two position. This is sterically more hindered due to this CH2 group. Now between these two methyl group which will oxidize. So now we have to see the steric interaction. So this is the transform this methyl 2 in transform methyl 1 in cis form. So between trans and cis form, the cis is sterically more challenged because interaction is there. This hydrogen and methyl steric hindrance is there. So that's why this is not sterically free, but this methyl is sterically free. That's why it first oxidized in presence of selenium dioxide condition. So this will not happen. This is also not happen. So this is also not. So the trans methyl oxidized to alcohol in presence of selenium dioxide condition, the allylic position is oxidized to alcohol. So the mechanism goes through in reaction followed by 2,3 sigma tropic rearrangement. Now the next question is find the current reagent for the reaction. So what is happened here? This glucose molecule, this PMB group is deprotected to alcohol. So what is PMB group? PMB is paramethoxybenzene. This is the benzene CH2PH, and if the para position is substituted by a methoxy group, then this is called as paramethoxybenzene or PMB. Now this is deep protection. So the benzene deep protection was done by DDQ. So there are three possibilities. This is also benzene, this is acetate, this is benzoyl COPH, but selectively deep protection happened in the case of PMB group. So in the sodium methoxide cases, this acetate group COCH3 is there, or COPH will deprotect. In the TBAP cases, there is nothing. TBAP is a deprotecting agent of silyl group such as ROSI Me3. So silyl is deprotected by TBAP. Triethylamine is base. This is also not amine. So DDQ is the correct answer. So, but if we see carefully, then benzyl group is remain as such, but PNB group is reprotected. So, how can we explain this? In the DDQ cases, I have shown the mechanism how benzyl group is reprotected by DDQ. So, if we know the mechanism, so it will goes through single electron transfer or free radical pathway. What happened first? This PM I am writing ROH PMB. First oxonium ion will pop. First oxonium ion will form. This one. After that, addition of water molecule will imply this oxonium charge. Sorry, simply taking this oxonium will pop, and now addition of water molecule take this product, this alcohol. So now, in case of benzyl and O-paramethoxy benzyl, see, the paramethoxy benzyl has a lone pair of electron. If we write this way, so this paramethoxy benzyl donates its electron to this oxonium ion and stabilize this oxonium carbocation. But in case of benzene, this not happen. So that's why paramethoxy benzene deprotected fast due to the electron donating effect of this paramethoxy group, which stabilize this oxonium carbocation. This will goes to which deprotection and this paramethoxy benzene converted to paramethoxy benzaldehyde. So the right answer will be DDQ. So DDQ will deprotect paramethoxy benzene to alcohol. So the next question is this one. DDQ in benzene. This compound in presence of DDQ undergo all single electron transfer reaction and form this carbocation. Now the lone pair of the alcohol attack to the carbocation to neutralize the system, which neutralize the carbocation and which form this one. Now this is the benzylic position. So this benzylic position is further oxidized in presence of DDQ by hydride transfer mechanism. So this hydride will transfer to the DDQ and forming double bond here with is nothing but the benzylic position oxidized. This is from this double bond. So this C is the right answer. Now the next question is this one. So now this is under DDQ oxidation. What happened? So first reaction proceed through benzylic hydride transfer mechanism. This in presence of DDQ. The hydride will transfer to the oxygen of the DDQ and from quinone to quinol. This carbocation will come and quin quinol going to this quinone form O minus Cl Cl nitro. Now this O minus abstract this proton and utilize this carbocation, secondary carbocation. This will form this double bond. Now this position is allylic now due to this double bond. This is the allylic position. So we all know allylic and benzylic carbon oxidized in presence of DDQ. So now there is a possibility of hydride transfer mechanism. So now presence of DDQ. This hydride will transfer and form this carbohydrate. Now there is a possibility of 1,2 methyl migration. So now this methyl group can migrate here to this carbocation. So 1,2 methyl migration giving so 1,2 methyl migration giving this one methyl methyl positive. So this is the secondary carbocation. This is the tertiary carbocation. So the second between secondary carbocation and tertiary carbocation is more stable than the secondary carbocation. That's why it is more stable and remain in this form. With like clean this. Yes, give me a second. What happened is there between this carbocation and this carbocation. Between these two carbocations, this carbocation and this carbocation. So this is tertiary and this is secondary. The tertiary carbocation is much stabler than the secondary carbocation. Government is here. So that's why it goes to this form after 1 to methyl migration. So now in presence of this DDQ goes to quinol form. Now there a proton is there. Now this O minus abstract this proton and neutralize this carbocation. It will form this one. I think this is clear. So the right answer is this one. So after DDQ treatment, methyl migration, 1 to methyl migration, giving this product. Now the next question is the can sodium ammonium nitrate, potassium bromide, dioxin water. So in the study of the can, I discussed about that the benzenic position. This is the benzenic position. So benzenic position is oxidized by can. So it oxidized the benzenic position with alcohol to single electron transfer mechanism. So as this is the tertiary alcohol, so it can't either oxidized to ketone or acid. That's why it's remain in the say this form. So the right answer is this one. So this is the primary disposition, but in these cases, this option and this option is not possible because CAM is unable to oxidize the primary position or methyl to CH2OH. This is the ketone is forming. This is also not possible in presence of CAM. So this is the today's lecture problem solving class. So, if I summarize this, so first I discuss about the sodium ammonium nitrate oxidation reaction. So when I discuss about sodium plus 4 goes to plus 3 and oxidize in alcohol or benzylic or allylic position to aldehyde ketone or ketone. So and the reactivity order, the secondary alcohol oxidized fast than the primary alcohol in presence of sodium ammonium nitrate. So it also oxidizes the arylic and benzylic alcohol. So to regenerate the catalyst and to maintain the catalytic cycle, we use TEMCO or sodium bromate. This is the benzylic oxidation and this is the allylic oxidation by CAN. We also discuss the active allylic or benzene position also oxidized by CAN. So this is the benzene position, benzylic position. So it is oxidized to alcohol and from alcohol. So this is the active methylene group. Active methylene group also oxidized to ketone in presence of CAN. Next we discuss next I discussed about DDQ mediated oxidation. So DDQ is 2,3 dichlorobenzene. So it first oxidized or aromatized the unsaturated ring to saturated ring. Then allylic or benzylic position is also oxidized. Deep protection is the main or one of the very important use of DDQ. So deep protection of any benzene or PMB paramethoxybenzene, deep protection was done by DDQ. Then I discussed about the selenium dioxide mediated oxidation. So benzylic or allylic position is oxidized by selenium dioxide through in reaction and 2,3 sigma tropic rearrangement. Also alpha oxidation of any ketone can be done through selenium dioxide mechanism. Same mechanism proceed. So if I draw the mechanism, is in presence of selenium dioxide. Further, rearrangement. So this goes to ketone or sorry, aldehyde. Now, next we discuss about the manganese dioxide mediated oxidation. So, any maleic or benzylic alcohol oxidized to aldehyde or ketone in presence of manganese dioxide. Also, oxidation of saturated alcohol was done by manganese dioxide. So, cis diol flipped to aldehyde in presence of manganese dioxide. Next, I discuss about the silver carbonate chloride mediated oxidation. So, this is nothing but Pretigen reagent. So in the second allylic or benzylic alcohol first oxidized, then secondary alcohol, then primary alcohol. So this is the selectivity order. Then I discuss about the late repeat reagent, that is the tetrapropyl ammonium carbonate reagent. So it is also oxidized primary alcohol to aldehyde. Next I discuss about the DNP oxidation. So it also oxidized primary alcohol or allylic alcohol to aldehyde. Next, I discuss about some problem solving class. These are the problem. So the first, due to the 1,3 interaction of the cis form, the mediated oxidation happened from the up phase, or in case of transform, no such interaction is there. So that's why it happened to the down space. So these are other problem which I discuss. Thank you for your kind attention for this class. So if you have any question, you can ask me. I am closing the class. If there is no such question, then I'll close the class. Okay, then bye.